everyone, welcome to Physicatube. This is third part of MCQs of Statistical Physics and Thermodynamics, and I hope this video will be helpful for you. Watch the video till end because all the questions are important. So let us start with the first question. The first question is, according to Maxwell distribution of molecular speed, the ratio between root mean square speed VRMS and most probable speed VP is. So here we have to find the ratio of VRMS and VP. What is Maxwell distribution of speed? This is the graph of Maxwell distribution, which is velocity versus fraction of molecules. For a particular temperature T, the graph is like this. So here this fraction of molecules carry the maximum speed. So this is called most probable speed, which is VMP. This is the speed which is carried by maximum fraction of molecules, and this is average speed V bar, and the highest speed is VRMS. So first of all we will write the formula for all the three speeds. So most probable speed is equal to 2 kT over m, where k is Boltzmann constant. Then V bar or V average is equal to, and RMS speed V RMS is equal to, here we have to find the ratio of VRMS and VP. So when we divide VRMS with VP, we will get the answer equal to root 3 by 2. So answer is A. Next question is, which of the following is not applicable to Bose-Einstein distribution law? So the statistics can be divided into two categories, with one is called classical statistics and second is quantum statistics. And quantum statistics is further divided into Bose-Einstein statistics and other is Fermi-Dirac statistics. And classical statistics is called the Maxwell-Boltzmann statistics. Now let us discuss some points about these two statistics. One is classical. Here this treats the particles as distinguishable, and quantum statistics, whether it is Bose-Einstein or it is Fermi-Dirac, it treats the particles as indistinguishable. This is the first difference. And second difference is, in case of classical statistics, we are free to choose any volume of or any size of the cell, and in case of quantum statistics, the cell size has a volume of h cube. It can never be less than or greater than h cube. So we can say in a way that in Bose-Einstein statistics, the cell size is equal to h cube. And if we have a look at these four options, so A is particles are indistinguishable. This is true for Bose-Einstein distribution law. B is size of cell can be less than h cube, but this is not true for Bose-Einstein statistics. So option B is the right answer. And other two options are, we know that in case of Bose-Einstein statistics, any number of particles can occupy single cell in phase space and all the particles have integral spin. And in case of Fermi-Dirac statistics, no two particles can occupy the same cell because they obey the Pauli exclusion principle, and the particles have half integral spin, like electrons, protons, neutrons. These all are fermions, and like photons are bosons. So all the three options A, C and D are true for the Bose-Einstein distribution law. Only option B is incorrect. Question number 3. In case of a system of identical indistinguishable particles obeying Pauli exclusion principle, the number of particles in each state epsilon at temperature T is proportional to. So as we know that quantum statistics can be classified into two categories. One is Bose-Einstein statistics and other is Fermi-Dirac statistics. And all the particles which are identical and indistinguishable obey the quantum statistics, and the particles which are having integral spin are called bosons. They obey Bose-Einstein statistics, and the particles which have half integral spin are called fermions. They obey Fermi-Dirac statistics. And one more difference is, in case of bosons, any number of particles can occupy a single energy state, but in case of fermions or in Fermi-Dirac statistics, not more than one particle can occupy a particular energy state, and the formula of number of particles in a particular energy state epsilon is given by 1 over e power epsilon minus mu over kt plus c. So this is the common formula for all the statistics. When c is equal to 0, then this formula is for Maxwell-Boltzmann statistics. When c is equal to minus 1, then this formula gives number of particles in a particular state for the Bose-Einstein statistics, and when this c is equal to plus 1, then this formula gives the number of particles in particular energy state for the Fermi-Dirac statistics. And for the Fermi-Dirac statistics, this mu is equal to epsilon f, that is Fermi energy. So it means the formula for Fermi-Dirac statistics means for the particles obeying Pauli exclusion principle is given by option A. Next question, coefficient of viscosity of a gas is. So now first is, what is viscosity of a gas? Whenever a gas is not in equilibrium and it is flowing parallel to xy plane, then velocity of gas in a particular layer which is parallel to xy plane is same. So in a particular layer the gas molecules have the same velocity, but as the value of z changes like this, the velocity of layers also changes. A layer which is moving with high velocity, it loses some of its momentum to the layer which is moving with lower velocity, or we can say that a slow moving layer exerts a frictional force on the neighboring fast moving layer and tends to slow it down. So it means the phenomena of internal friction between the successive moving layers in a gas produces a velocity gradient in the gas. That velocity gradient is called viscosity of the gas. And formula of viscosity is given by this expression. So from this expression we observe that viscosity is directly proportional to square root of temperature. So correct answer is option B. Also the viscosity is independent of pressure of the gas, and here K is Boltzmann constant, M is mass of the gas, and D is the particle diameter or molecular diameter. So eta is directly proportional to root m over d square also. So in this case the answer is option B. Next, at a given temperature, which of the following has lowest thermal conductivity? So from the kinetic theory of gas, the thermal conductivity is represented by lambda, which is equal to, so in this formula of thermal conductivity, F represents the degrees of freedom, D is the particle diameter, K is the Boltzmann constant, T is temperature. So thermal conductivity is directly proportional to root T like viscosity, and lambda is inversely proportional to root m. So it means thermal conductivity of a heavier gas is lowest and of a lighter gas is highest. So out of the given options, hydrogen has maximum or highest thermal conductivity, and as oxygen is heavier gas, so oxygen has lowest thermal conductivity. So correct answer is option D. Next, a steam engine is operated when steam at atmospheric pressure and 100 degrees Celsius. Steam leaves the engine at slightly above outside temperature 35 degrees Celsius. What is the efficiency of the engine? So formula of efficiency is 1 minus temperature of sink over temperature of source, and in this case the temperature of sink is 35 degrees Celsius because temperature of sink is always less than temperature of source, and temperature of source is 100 degree Celsius, and we will convert the temperature into Kelvin by adding 273, and when we solve this we will get the answer 0.174, which means the efficiency is 17.4%. So option D is correct. Next question, 2 moles of an ideal gas at a pressure of 1 into 10 raised to power 5 Newton per meter square has 400 joule of heat added in expanding from a volume of this to volume this, what is the amount of work performed? So we know the formula of work performed, that is equal to P dV, where P is pressure and dV is change in volume. So if this is volume V1 and this is volume V2, then dV is equal to V2 minus V1, and the pressure is also given. So when we substitute the values and solve, we will get the answer equal to 230 joule. So option B is correct. Next question, what is the change in entropy for 10 kg of water going from liquid to vapor at 100 degrees Celsius? The heat of vaporization of water is given, that is equal to this. So change in entropy, we know its formula, that is dq over T, where dq is equal to ml, where m is mass of water and L is latent heat of vaporization, divided by T. Substituting all the values, mass is 10 kg, L is, and temperature is 100 degrees Celsius. In Kelvin it is equal to 100 plus 273. We will convert it into Kelvin because the answer is given in joule per Kelvin. So when we solve this, we will get answer 8.847 into 10 raised to power 3 joule per Kelvin. So option B is right. Next question is Thomson coefficient is. So we have to write the formula of Thomson coefficient. Before that, let us discuss what is Thomson effect. When current passes in a conductor whose two ends are at different temperatures, then heat is either evolved or absorbed depending upon the direction of flow of current. For example, we have a copper wire. This end is hot, means at a higher temperature, and this end is at lower temperature, and current is flowing from higher temperature to low temperature, means this end is at higher potential and this end is at lower potential. So in this case the heat will evolve, and if we reverse this phenomena, means if this end is cold and this end is hot and current is flowing from cold to hot, and then it will take place with the absorption of heat, then heat is absorbed in this case. So it means this is called Thomson effect, and formula of Thomson effect is given by option B, T square E over dt square. It is represented by sigma. Next question is canonical ensemble is a collection of essentially independent systems having same E is energy, V volume, N number of particles, T temperature, and mu is chemical potential. So the ensembles can be divided into three categories. First is the micro-canonical ensemble. In case of micro-canonical ensemble, the system that is under consideration is isolated. It means number of particles and the energy of the system is fixed, and as you can see, volume is already fixed. It is given in all the four options. So if we have E, N and V fixed, we have a microcanonical ensemble. So option A is for microcanonical ensemble. Now what is a canonical ensemble? If the system that is under consideration is in thermal equilibrium with the heat reservoir, let us consider that this is a system, and in this number of particles and volume is fixed, but it is in thermal equilibrium with this heat reservoir. So it means its temperature remains constant but energy is not constant. So if we have N, V and T, that represents canonical ensemble. So option C is for canonical ensemble. And third is grand canonical ensemble. In a grand canonical ensemble, the system that is under consideration, it is in contact with both the heat reservoir and particle reservoir. So it means it can exchange the number of particles with this reservoir, and also it can exchange the energy. So energy and number of particles are not fixed in grand canonical ensemble, but the temperature is fixed. So T is fixed and the chemical potential mu is also fixed. So mu, which is chemical potential, is the energy required to add a particle into the system. So in a grand canonical ensemble, T, mu and V, these three are fixed. So option B represents grand canonical ensemble. So in this case we have to find the condition for the canonical ensemble. So option C is the right answer. Next question is partition function is. So here we have to find the partition function of canonical ensemble, which is represented by Z, and in some books it is represented by the symbol Q, and its formula is equal to summation e power minus beta ei, where ei is the energy of ith state and beta is equal to 1 over kT, where k is Boltzmann constant. So this is the formula of partition function. So option B is correct. Next question is entropy change in reversible adiabatic process. So in case of adiabatic process, we know that delta Q is equal to 0 because no heat can enter or leave the system. So if delta Q is 0, delta S is equal to 0 means there is no change in entropy in an adiabatic process. Moreover, in case of reversible process also, delta S is equal to 0. So here the right option is B. There is no entropy change. Next is in canonical ensemble. So 4 statements are given and we have to choose the right statement for the canonical ensemble. So as we have already discussed, in case of canonical ensemble, N, V and T are constant. It means the number of particles are constant or well defined, volume is constant, and also the temperature is constant. It means the system which is under consideration, it is in thermal equilibrium with any heat reservoir. So it means the energy of system is not constant but temperature is constant. So out of these 4, the right answer is option A, means system is in thermal equilibrium because temperature T is constant and also the number of particles N are well defined. So option A is the right answer. Next question is which of the following relation is true? In case of canonical ensemble, the partition function is given by summation e power minus beta epsilon I, and the formula of energy of canonical ensemble is, or we can write it as minus 1 over z curly z over curly beta, means derivative is with respect to beta, but in option C the derivative is given with respect to V, that is volume, and also at constant volume. So this is not possible because at constant volume we cannot take derivative with respect to volume. So option C is incorrect. This relation is not true. All the other 3 relations, entropy and Helmholtz energy and Gibbs free energy, are correct for the canonical ensemble. Next, the Planck's radiation law and Rayleigh-Jean's law become identical if. First of all, what is Rayleigh-Jean's law? Rayleigh-Jean's law gives the spectral energy density of a black body radiation. Spectral energy density means energy per unit volume in the frequency range nu to nu plus d nu, which is given by the formula u nu d nu is equal to 8 pi nu square over c cube kt into d nu. Here energy associated with every mode was taken as equal to kt, which is classical energy. In this formula, when frequency is very high means nu tends to infinity, then energy density u nu d nu also tends to infinity. But experimentally it was found that at very high frequencies u nu d nu tends to 0, and this was called ultraviolet catastrophe. So after that, Planck has given Planck's radiation law by considering that energy associated with electromagnetic mode is quantized, and it is given by h nu over e power h nu over kt minus 1. And for the Planck's radiation law, the energy density u nu d nu is given as 8 pi nu square over c cube, which is same as the first term in Rayleigh-Jean's law, and this kt is replaced with this energy. So according to Planck's radiation law, when the frequency is very high means h nu is very greater than kt, then what happens? This term in the denominator becomes very large. So that is why u nu d nu approaches to 0. Means there is no ultraviolet catastrophe in this case at very high frequencies, as it was in case of Rayleigh-Jean's law, because in Rayleigh-Jean's law when frequency is very high then this u nu tends to infinity, and in this case for high frequencies this term tends to 0, which agrees with the experimental results. And when h nu is very less than kt, in that case the denominator term e power h nu over kt can be expanded, because this power becomes very small, and it can be written as 1 plus h nu over kt. We can expand the exponential term up to the first order. So when we substitute this value in this equation, minus 1 and plus 1 cancels out, and in the denominator we have h nu over kt, also h nu cancels out, and we will get this term again, 8 pi nu square over c cube into kt. So it means for this condition the Planck's radiation law reduces to Rayleigh-Jean's law. So in other words, in terms of temperature, we can say that when temperature is very high, because kT is very greater than h nu, so when temperature is very high, in that case Planck's radiation law becomes identical to Rayleigh-Jean's law. So right answer is option C. And the last question is, a body cools down from 67 degree to 62 degrees Celsius in 5 minutes, and it will cool down from 62 degrees Celsius to 57 degree in. So we have to find the time which a body will take when it cools down from 62 to 57 degrees Celsius. And here we will apply Newton's law of cooling, that is dT over dt means change in temperature with respect to time, and since there is cooling, so we'll take minus sign, is proportional to difference of temperature of the body and the surroundings. So here the temperature of surrounding T naught is not given, so we can take value of T naught equal to room temperature, which is equal to 27 degrees Celsius. So the formula can be written as minus dt over dt is equal to, by removing this proportionality constant, let us say the constant is K, T1 plus T2 over 2, which is temperature of the body. Like in first case T1 is 67 and T2 is 62, minus T naught. So now we will substitute the values in the formula. So for the first case, dt is the change in temperature, that is temperature becomes 62 degree, that is final temperature T2, and initial temperature is 67 over dt, which is time taken, that is 5 minutes, equal to K. T1 plus T2 is 67 plus 62 over 2 minus T naught. So left hand side it is equal to 1, right hand side is K, this is 64.5 minus T naught. So from this expression we will find value of K, that is equal to, now let us consider the second case where body cools down from 62 to 57 degrees Celsius. So T2 is 57 minus 62 over time, we have to calculate dt, and this is minus sign, equal to 57 plus 62 over 2 minus T naught into K. So here we have to find dt. What we will do, we will substitute value of K from this expression, and we will consider T naught, that is temperature of surrounding, equal to 27 degrees Celsius, and when we solve this we will get value of dt approximately equal to 5.7 minutes, means time taken in cooling from 62 to 57 degrees Celsius is greater than 5 minutes. So option C is correct. And there is other way of attempting this question. If you don't want to waste your time in all these calculations, then you can simply guess the answer of this question. The way is, we consider that temperature of surrounding is 27 degrees Celsius. So when a body cools down from 67 to 27, the temperature difference is around 40 degree. And in the second case, the body starts cooling down from the temperature 62 degrees Celsius, and since temperature of surrounding is 27 degrees Celsius, so here approximately the temperature difference is 35 degree. So more the temperature difference, लेस द टाइम द बॉडी विल टेक इन कूलिंग डाउन। यहाँ पे जो टेम्परेचर डिफरेंस है सराउंडिंग एंड बॉडी का दैट इज़ मोर, सो यहाँ पे जो कूलिंग है वो ज़्यादा फास्ट होगी। और इस केस में जब बॉडी 62 से 27 पे आएगी, सो इस केस में क्या होगा कि टेम्परेचर डिफरेंस दोनों का कम है एज़ कम्पेयर टू द प्रीवियस केस। तो यहाँ पे जो कूलिंग है वो स्लो डाउन हो जाएगी। तो जितना भी सराउंडिंग और बॉडी का टेम्परेचर डिफरेंस ज़्यादा होगा उतनी ज़्यादा फास्ट कूलिंग होगी। सो यहाँ पे हम अगर यहाँ पे इस केस में 5 मिनट लग रहे हैं, सो व्हेन बॉडी कूल्स डाउन फ्रॉम 62 टू 57, तो इस केस में टाइम ज़्यादा लगेगा। सो ऑब्वियसली इट विल बी मोर देन 5 मिनट्स। सो इन दिस वे you can also guess the answer of this question. That is all about the MCQs of statistics and thermodynamics. I hope you have enjoyed the video, and if you do, then please like the video and also subscribe my channel. Thank you for watching.